Hi everyone, my name is Konstantin and today I want to give you an introduction into the Global Energy System Model, or GENeSYS-MOD for short. This is the first out of an online workshop series that will cover 4 workshops in total, plus 1 general introduction into the model. The workshops will essentially teach you how to use the model, how to install them, how to run them, how to understand the outputs, and how to understand the output data as well. The workshop today will essentially cover the installation process, downloading a sample data set, and then running the model for the first time. As I mentioned, there will be 5 workshops in total, 1 workshop on the general background, and then 4 workshops on how to run and use the model. And today we will go into an introduction, into the settings, and some hands-on exercise that you can perform yourselves. The workshop today will cover a brief look into the structure and workings of GENeSYS-MOD from a code perspective. So I will give you a short introduction essentially and show you some slides on how GENeSYS-MOD is built, how it's structured, and how it works. And then I will give you an actual hands-on introduction into how to run the model, extract results, both in GAMS and other formats. And an introduction into the different settings and their functionalities. At the end of this workshop, you should understand the basics of the model structure and scope, and you should be able to run the model on your local machine. Plus, you should know how to change some key model settings, which doesn't really require any modeling involvement or modeling background. It's very easy to change some key functionalities, essentially just by using some of the provided switches. And you should have some knowledge on how to extract result numbers out of the model. So, to give you a little bit of an introduction into GENeSYS-MOD in general, the model is a linear program with a focus on sector coupling, and it's minimizing the total system costs over a certain period of time. Usually we're looking roughly into the area 2050 in terms of future energy system developments. For this, the model takes various input data points. On the left-hand side here, you see inputs into the model. And then in the middle, you see the actual model part. And on the right side, you see the outputs. Common inputs into the model are, for example, things like demand data points. So both in terms of absolute numbers over the year, that means a certain amount of kilometers for passenger transport, for example, but also time series of demand. So for example, how much mobility is being demanded. An important factor is also the renewable potentials. So we have to include how many gigawatts of installed capacity can be actually placed in a certain region. This is quite important. Also, for example, things like biomass availabilities play a huge role. Also important is weather data, especially if we look into highly renewable energy systems. This means that we actually require a lot of weather, but also then demand time series data that is fed into the model as well. We always start our model in a base year, so we always start with a pre-existing system that is then optimized towards the future. And essentially it builds on these information that it has. So we need information on the capacities in the base year to know essentially where we are starting from. Also, we have to include some political targets if there are any. For example, fossil fuel phase-out dates or renewable targets or CO2 emission constraints or something like this. Those can also be all fed into the model. And the last point, it's actually going beyond fuel prices, it's cost data in general. Since it's a cost optimizing model, of course, cost data plays a huge role in the computation and the results. So in the end, both fuel prices, but also technology learning curves and so on are highly relevant when it comes to inputs into the model. The model then optimizes the energy system across the different sectors. Usually the sectors electricity, heat in both buildings and industry, and transportation are considered. Heat and transportation are then split into different subcategories. For industrial heat, so for process heat, it's split up into low temperature, medium temperature, and high temperature applications. And for transportation, it's split into passenger and freight transportation demand. Then we consider a plethora of different technologies on the supply side. So we have either conventional generation, such as nuclear power or fossil energy carriers, but we of course also feature a wide range of renewable energy sources. All of these then create different kinds of fuels that then either go into, for example, electricity demand directly, or go into, for example, by burning fossil fuels into heat directly. But of course, there's also a huge amount of sector coupling, either by direct electrification, so if we use electricity to then supply heat to buildings, or via indirect electrification, so for example, going through hydrogen, either by using fossil energy carriers like steam methane reforming, for example, that uses natural gas to generate hydrogen, but also, of course, through means of electrolysis to generate green hydrogen that can then be used in the different sectors as well. What we get out of the model are then information on primary energy demand. So essentially demand developments on the primary energy side, but also on the final energy side, so sectoral demands. Since we consider some sectors as a proxy fuel, essentially, for example, a transport, we don't give it a final energy demand for transport. Instead, we have a certain demand for the service transport, so a certain amount of kilometers traveled. And this means that final energy demand in transport, for example, is then optimized within the model. And we can get these numbers out of the model as well. We will get the time series of technology investments, so essentially the capacity expansion plans that the model deems cost optimal. We get the renewable generation mix and in general the energy mix, essentially the energy dispatch for our time frame. And this, of course, means that we can then infer from this information fossil fuel phase-out dates, for example, points in time when fossil fuels are simply disappearing from the mix, and of course also things like CO2 emissions, emissions trajectories. If we've set carbon constraints, then we can usually see shadow prices for CO2 costs, for example, as well. So this is roughly GENeSYS-MOD from a very brief side, very stylized, very undetailed. If you want to have more information on this, there will be another webinar which focuses specifically only on model applications. It goes a little bit more into technical detail in terms of technologies and so on. Today we will mostly cover how to run the model, so this will be essentially it. So I will refer you to the other workshops instead. From a more technical side, GENeSYS-MOD is currently still based in GAMS. We are currently still in development of a Julia version, which will be available, and if it is available, I will link it down in the description. It will most likely be available at some point during 2023. Currently, as I said, GENeSYS-MOD is constructed in GAMS, and this means that the file endings are always .gms for GAMS files. In total, we have a multitude of files that essentially construct the model. The main function of GENeSYS-MOD is the GENeSYS-MOD GAMS file. And as a non-proficient user, as a first-time user, this is usually the first and only file you will need in the beginning. The GENeSYS-MOD GAMS file is the one that calls all the other files and essentially reads them in the correct order, and then essentially passes on information and so on. So one file that comes after the GENeSYS-MOD GAMS file is then the declaration file, where all the different parameters and variables and sets are defined. Then follows a data load file, which essentially reads all the files from all the data points from the Excel input files. Currently the input is handled via Excel files. I will go into that in a moment. Then after the data load, there comes the bounds. This is essentially a definition of reference values like default values and some very basic calibration in the beginning, followed by a file that's called GENeSYS-MOD settings. And the GENeSYS-MOD settings are then for overall settings as a relevant, essentially, model parameters, things like which years to consider, things that are usually not changing too much and therefore are not in the Excel file, but instead settings that you can set in GAMS. The GENeSYS-MOD equation file, GENeSYS-MOD underscore EQ contains all the equations of the model and therefore contains the actual mathematical model formulation. This is essentially the main part of the model. After that is the output data processing. So this is the GENeSYS-MOD results GAMS, where essentially then the model results are being parsed and put into different output file formats. You can output them either as CSV files, but also Excel files or GAMS files are possible. So it's possible to either use a results or an Excel result output essentially. Some additional files that can be used but do not have to be used are, for example, scenario data for a specific region. So if you're calculating a model, for example, for the region Europe, then you can define a GENeSYS-MOD scenario data Europe.gms file, which would then contain specific constraints or limits or calibration tools for that specific region. So in this case, it would be for Europe, for example. If you have certain constraints in some way that are not present in the general equations, then you can put them in this file. This is always being read in via essentially this region coding here. Then another file is the GENeSYS-MOD subsets.gams file. These are definitions of subsets, which make handling a little bit easier because then equations can be constructed only for these specific subsets. So this is a file that contains different lists of, for example, technologies that are then subsets of the entire set of technologies. And one file is the GENeSYS-MOD interpolation file. This is essentially just to fill in blank spaces if you have forgotten values in between years, for example. So if you have added 2022 as an intermediate year between 2020 and 2025, and you forgot some values for demands, for example, or so on, then this script here will essentially cover this for you and instead insert the values as a linear interpolation. So this is just more of a helper file. Going essentially in the same, like this graph here shows the same structure, but more as a flow chart then, what is happening in which time. As I said, the main function is in GENeSYS-MOD GAMS. So this is really the main file where also most of the basic settings are defined. For example, also which data files are being read in. This is then passed onto the declaration file, which then reads the data load file. The data load file then covers the subsets as well and goes into the time series reduction algorithm. In the end, GENeSYS-MOD relies on hourly input data. This means that every input data format should be hourly. But in the end, usually the actual computations are not based on an hourly approach, simply because otherwise it would exceed the computational requirements, or availabilities rather. The requirements would exceed the computational availabilities. So the GENeSYS-MOD time series reduction GAMS file essentially calls a time series reduction algorithm, which reduces the time series to a flexible amount of time steps. So this can be chosen by the user depending on their computational availabilities, essentially. Then everything is passed onto the settings file, which then is then followed by the interpolation file. There's also one file that allows you to aggregate multiple regions into one region if you wish to do so, for example, for some basic testings. Then the bounds are read in, then the scenario data as a last step before the equation. So this is really also if you want to override some stuff that is because of some region-specific issues. Then the actual constraints are constructed, and then the model is being solved. After the model has been solved, everything is passed onto the result script and then being output, essentially. You can also see the legend for the different functional groups and files here. You can see which files are mandatory and which files are optional, and also which belong to a functional group. So we essentially have the main function, then data read-in, model calculations, and then outputs, essentially. Okay. GENeSYS-MOD, as I mentioned, uses Excel files to read in the data. This is mostly to make it more user-friendly, since most people are actually quite proficient with Excel, and it provides a nice user interface for the data points that we generate. So at least on the input side, we're using this Excel file format, and we read from 3 different input files. We always have one global data file that contains all information that is relevant for all regions. So this means, for example, general technology data. This means something like investment costs for the different technologies, because we consider that those are usually the same across the globe, or at least that's what we have data for. Otherwise, we have a regional data file that contains the region-specific information. So, for example, energy demands for the region that we're looking at, for example, but also other things like emission constraints. You can define different emission limits. You can either have annual emission limits, either for the entire region or for the sub-regions and so on. And then we have an hourly data file that is also essentially a regional file that contains all the time series used by GENeSYS-MOD. So, for example, all the renewable generation time series or the load curves. So demand time series essentially as well. This file is usually then by far the largest, which is why it's also split up into these different files essentially to make handling a little bit easier. The data reading logic is as follows. The model always tries to read information on the specific region it's looking for. So it would always be looking for, in this case, in the Middle Earth example, it would always look for the data in the specific Middle Earth region. But if it can't find data, then it will use the global data instead to fall back essentially on. So this is always the idea, that you always have this fallback option. The hourly data then, as I said, is specific for this very region. There's no fallback option or anything like this. You can find GENeSYS-MOD on its public GitLab page. There's a public Git where you can download the source code as well as some example data and a quick start guide as well as a technical manual. So there is documentation provided there. As I mentioned, there will be a Julia version coming up, and then most likely the GENeSYS-MOD Git will move to a other location. If that happens, I will update the links in the description, but there will definitely be a public source for GENeSYS-MOD, both in GAMS and in Julia available, with a proper documentation. The dataset used for this workshop series is the GENeSYS-MOD Middle Earth test dataset. It's specifically generated to test the model and to make it more understandable with a smaller size dataset for new users. And this is what we will be using today. Essentially, we have 5 nodes in total, and we will essentially look at all the features of GENeSYS-MOD within these 5 nodes. Right. General model settings can be found in the GENeSYS-MOD.gams file. The GENeSYS-MOD.gams file, as I mentioned, essentially contains all the instructions for GAMS to know what to run, and it contains also the most relevant settings that can be called essentially immediately in the first file without having to dig through the equations or anything. This is therefore something like the heart of GENeSYS-MOD. You will see a header for all the files where you see essentially information on the copyright and so on. It's released under the Apache license 2.0. And then just below that, you will see these kind of switches here. It's always in the format where it says if not set, then a name, and then set global, and then essentially a statement. The idea here is that it checks if it has been set before. This means that if you set it otherwise via command line, for example, if you're running things on a compute environment or so, on some cluster computer, then you can essentially set the values for the switches exogenously outside of the actual GAMS runtime. You can actually set it from the outside, give it in, for example, a batch file or some job file on a Unix cluster, and then set these values from there, and then, for example, calculate different sensitivities by you doing so. If you don't give it a value from the outside, then it will refer to that value that you give it on the right hand side here. So essentially, if it's not set, the switch Unix path, then it will set switch Unix path to 0. And what this switch, for example, does is it's essentially converting file paths from Windows to Unix. So if you're on a Windows machine, then you want to set it to 0. If you're on a Linux machine or a Mac machine, then you will want to set it to 1. This is more of like a technical setting. This is something that you will most likely not have to change from time to time once you found your correct setting, but other settings might be. So for example, there's one switch, that switch invest limit, for example. This here essentially determines if a set of constraints that focus on sector change limits and investment smoothing constraints, essentially, if they are to be considered or not. So these you can always use to enable or disable something. For example, the third one here, switch CCS, that's pretty much as the name suggests. You can choose to set CCS technologies to be available or not available. There is a full list of these switches in the technical guide, so you can just go to our public Git and look at the technical guide if you want to know what each switch does. We're always trying to have our names to be as clearly as possible, so that you don't need as much documentation, but of course it's always possible that something is not quite clear, but there should be documentation for it. Otherwise, you're always free to send us a message to essentially ask for support if you don't understand something specifically. Right. After the GENeSYS-MOD GAMS file, there's another place where you can do some general settings, and this is the GENeSYS-MOD settings.gams file. This file essentially opens additional settings in GAMS instead of Excel. So that's usually values that you use or change, for example, for sensitivity analyses, to make it easier than changing the Excel files all the time. Because the issue with Excel is usually it takes a while. You need to open a separate program. Excel files also don't have proper version control if you're working in a Git environment. So this just makes it much easier to do some operations if you do it immediately in GAMS. And this allows you to do some modifications to the model scope on the fly, essentially. So some general settings like the discount rates, or as I mentioned before, the amount of years that you're considering in your calculations, you can set them in the settings file. So essentially, if you set a year here to no, then it will be removed from the set of years that is being calculated. This means that in the end, the model, of course, runs a bit faster. It's less complicated to run the model. And if you're not interested in, for example, 5-year steps anyway, then this could be, for example, a good way of reducing model complexity in that case. All right. So this much as like a general input on just like the theory. Now we can jump into an actual hands-on exercise. And for this, I have uploaded data on the website called GENeSYS-MOD workshops.postcarbon.energy. And if you click that, it will open the browser on like the TU Berlin cloud. And there you will find all the different supplementary materials essentially to use for these workshops. What you will find there is the GAMS installation. If you require it, you can just download it from the GAMS website, but I've just placed it here to make it a little bit easier for you. Also, there's the GENeSYS-MOD Middle-earth version 2 example. It's essentially the same as on the public GitLab. You could download it from there if you wanted to, but it's in there. There's also a list of all the GENeSYS-MOD technologies with a description what they are essentially. And then you will find for each workshop, you will find the presentation slides essentially as I've presented them today. So you're able to find everything on here. What we need for this workshop is the GENeSYS-MOD Middle-earth v2.zip file. So you can just download this. And you need to have GAMS installed. So if you don't have GAMS installed, you need to either download this file or just download the most current version from the web. But in my case, I already have GAMS installed, so I don't need to do this. Once I have this zip file, once I have this zip file here on the desktop, I can just extract this here. And then I will have this folder here. This folder contains all the files that you need for today. What you will find there is essentially all the different GAMS files, the license, and a short README. So in the short README, you will find some very quick start guide, essentially on what the things do, some overview of the settings, and some general version history and so on. The different GAMS files are a lot more than has been presented. This is mostly because there are some intermediate files that do some stuff that is not quite relevant for today. There's also some scenario data present for things that we will not be looking at today. So for example, there's a scenario data for Europe. Today we will be running the Middle Earth example. The different other folders are batch files. In the batch files, there is a tool to merge the results. I will go into that in a second, or after we've actually run the model. But you can also place batch files to run the model in here. So if you wanted to, for example, run the model for another application, such as, for example, let's say a model on Europe or so, then this would be look something like this, where you could then create a batch file that calls GENeSYS-MOD GAMS from GAMS, and then you can give it all the commands that you would give it in the command line, essentially in GAMS, and then you can set all of these switches and outputs and so on in here, and then you could just run it essentially from the command line instead of running it from the GAMS development engine. Right. There's also a folder on documentation where you find the quick start manual and the technical guide. So you will be able to find both of them here. There's a folder called GDX file, which is just empty at the moment. This will be useful or relevant in a second once we run the actual model. There's a folder called input data where you will find the exact 3 files that I mentioned before. So you can find the data Middle Earth, the global data, and the hourly data, and we will go into them in a second. You will see a folder called results. This is essentially also just an empty folder for now. There is a result analysis script in the software Tableau if you have access to that. We actually use Tableau quite frequently to generate our result graphs because it's a very convenient way of doing so, since GAMS does not really provide any data visualization tools. If of course you are more proficient or want to use something like Python or Julia, you can of course just use the resulting CSV files that you get out of the model and just use them and read them in and create any graphs that you want. We are also currently working on a Python dashboard for the results that you can essentially just use, read the CSV files that we generate in the model, and then you can visualize the results with that Python dashboard if you don't have access to Tableau. Tableau is free for academic use and students, so you might have a look there. There's also a directory called temp files, which is currently empty. This one essentially saves all the mappings of the different data regions. This we will also see once we actually run the model. All right. So before we actually head into the GENeSYS-MOD GAMS file, I will very briefly open the input data. There will be a more in-depth workshop on the input data files in general, but I just want to briefly go over them. Let's start with the global data file. The global data file contains various different sheets that are being read into GAMS. The more central one is the sets. The sets essentially contain the list of all the different set entries. So for example, all the different technologies, all the different fuels, all the different years, time slices, modes of operation, the region, only world in this case. The other regions will come in and be read in the second data file. And then things like seasons, daytimes, daily time brackets, storages, and modal types. These are the sets that are being used in GENeSYS-MOD. And if you wanted to add a set entry here, you would do it here. The other sheets essentially contain all the different data points. There's always an explanation at the top, which essentially gives you the name of the parameter, for which dimensions it's called. So in this case, it's tag technology to sector, for T in technology and SE in sector. It assigns technologies to the different sectors, and the unit is just binary. So this is just a tag, and essentially it says that D battery lithium ion is part of the sector storages, and that P biomass, for example, is part of the sector power. This is essentially just a mapping of different technologies to different sectors. As I said, there will be a more in-depth tutorial on the data side, but essentially all the different sheets should be named and should be labeled. One thing that is also important are the different units. The units are always given. Energy units are always given in petajoules, and capacity units are always given in gigawatts. So there's, for example, then also a conversion between gigawatts to petajoules, for example, in terms of generation capacities to the amount of energy they can provide, and so on and so forth. For us at the moment, the most relevant parts are the sets, since here we see that there's only a world set, and this is, as I mentioned, since this file here contains the general technology data. So we will see, for example, the sheet capital cost. The capital cost, you will see the baseline capital costs, or the investment cost for the different technologies. There you would see, for example, for PV plants, for example, the investment cost for the different technologies that are then as a fallback option, essentially, that go for all the different data sets of GENeSYS-MOD. The second data file is then the actual regional data file. So this would be data Middle Earth in our case. And here the sets look a little bit different in a way that now we add the different regions. So it will have the same technologies and fuels usually. You can also add things if they are regionally specific. So you can actually add more fuels here that will then essentially add on to the list that has been read on in the world data file. But this specifically mostly adds the different regions, and this means that, for example, this here will then feature information like specified annual demand, and the specified annual demand is then the annual demand for each output fuel. And this is essentially then the sum of all hours, so this is a total annual demand. So this would mean, for example, that Rohan has an annual demand of roughly 1,950 petajoules of electricity that are then distributed to the different hours and time steps via the hourly time series, which we will look in a second. This workbook is essentially just a little bit bigger than the world one because it features more information. So here, essentially, if you ever wanted to change something in terms of input data, you want to add a new region and so on and so forth, it would be done in this sheet mostly. GENeSYS-MOD in general is very flexible in a way that it's a framework. It can run with a multitude of different geographical settings. We have used it as a global model with 10 macro world regions. We've used it as a European model with 30 regions across Europe. We've also used it as a German model with 16 euro regions for Germany plus neighboring countries, so 25 regions in total. And we've also used it down at a city level for Berlin, for example. So it's essentially mostly data-driven. In theory, you could go down even to the municipality, household level if you wanted to. But mostly it's aimed at rather large-scale, long-term energy system analyses. So usually something down to maybe like a city-state level or so is usually the envisioned context, with upwards being unlimited, essentially up to global applications, as I said. Right. So if we look at these demands that I mentioned, the different demands are then distributed to the different hours. So Dol Amroth, for example, which is a city-state in Middle Earth, has a total power demand of 165 petajoules. And if we look then at the hourly data for Middle Earth, we can then see how this is distributed across the different hours. So here we will see, for example, for load, which is then the electricity load, we can then see essentially how the demand is being distributed. And this is usually a time series that has an average of 1. And then essentially shows the deviation from the average value. So we would know that in the first hour, there's 85% of average yearly demand. In the end, all of this will be read into the model, and the model will do the right things essentially. It also doesn't have to be in this format. It can also be in a format that you give it the percentage of the total load, for example, so then you wouldn't have the average of 1, but the sum of 1 instead. All of this is quite possible. In the end, the model will always normalize this in the end anyway, so it doesn't need to be around 0 or 1 or anything anyway. Anything is possible. Here, for example, for temperature, you can actually see this. Here the values are not an average. Oh, they actually are an average of 1, so in this case it's actually the same. But I've also used temperature series that are like raw temperature series, and then the model will essentially use them and transform them into the right data format. So all of this works. What you will always find here is essentially the hour of the year. So this is the first entry here. So this is always between 1 and 8,760. And then there's always the field time slice. The time slice is essentially the other way of running GENeSYS-MOD that is more of a legacy formulation. As GENeSYS-MOD comes from Osmosis originally, Osmosis uses a time slice approach instead of a reduced time series. And these time slices are essentially predefined averages over certain categories of the year. So for example, would be something like summer day and summer night. And then you would essentially group all of the hours that fall in this category together. In our case, we have defined this as the different quarters. So it's essentially quarter 1 to 4 in the year. And then it has night, morning, peak, and afternoon hours. And all of these are essentially mapped in this column here. So if you're using this time slice based approach, then you can just essentially work with this formulation, and it will essentially use this information to then aggregate everything. Normally now we're rather using this hour-based approach, and you don't have to worry about these time slices here at all. You can just leave them in there, and it doesn't matter too much. Here you will see all the different time series. So in total we have different time series for PV. So we usually consider 3 categories for each renewable technology. For PV we consider inferior, average, and optimal placements, as well as access tracking PV. For wind we consider inferior, average, and optimal placements for onshore wind, which is essentially always categories of total placement options of wind, then grouped by essentially their average capacity factors. We have a time series for dispatchable hydro and run-of-river hydro. We have time series for offshore wind in the categories transitional, shallow, and deep. We have a time series for the load, so electricity demands, for mobility, for industrial heat applications, for building heat, and then efficiency curves for air source and ground source heat pumps. These are the different time series that you need to supply to GENeSYS-MOD. So once you have essentially everything set in the data files, and in our case you can just download them, as I said, it's already available, then it comes to the actual model. For GAMS, the easiest is then to open this project file. You always need a project file to make sure that you're running in the correct folder. So if you have GAMS installed, you can just double click the GENeSYS-MOD project file, and then it will open, and it will essentially look something like this. The important part is that the path that you have on the top here is the path where your actual download and your extracted data files are located. This is important. You can use either GAMS IDE or GAMS Studio. I personally still prefer GAMS IDE, even though it will be depreciated soon, and then I will not be able to use it any longer. But this is just personal preference, especially users that have never used GAMS IDE before might as well just use GAMS Studio. It just looks a little bit different, but it generally works exactly the same. And one important part is that you look at your solvers. So if you go to options, solvers, you will see if you have a license for the solver or not. You can essentially, during GAMS installation, immediately specify a license file, or if you have an alternate license file that you have somewhere else, you can just press this button and then navigate to your license file. So you will need to make sure that you have a GAMS license, and then essentially a license for at least one of the LP solvers. So we recommend either Cplex or Gurobi usually. These are the ones that have performed the best so far for our model. All right, then once we have essentially opened this project, we can press the Open File button, and then we will be offered all the different GAMS files. And for now, we will just focus on the GENeSYS-MOD GAMS file. You can just open this, and then what you will see is exactly what I had in the slides. So you will see some header, and then you see all the different switches. And the switches are actually quite long. So there's actually a quite long list of different settings and options that you can choose, that you can use to essentially immediately run different sensitivities. Some of the more important ones are CCS, the invest limit. If you have troubles with having an infeasible model, you can switch the infeasibility tags on. Those are essentially like slack technologies that can provide energy at a very high cost, but they are useful to essentially debug your model. The base year bounds, they essentially define production numbers in the base year that the model is calibrated to. So this is also for error handling. That's quite useful to turn on or off. Otherwise, what can also be used for sensitivities is essentially the peaking capacities. These are constraints that determine essentially the additional capacities that are needed to supply enough energy in peak load hours. Here you can set the solver. That's also a quite important option. So here you would decide between Cplex or Gurobi, for example, or if you don't have access to either, then you can use an open source solver. Of course, you could also use something like Skip or so. Also important are the settings for the data files. So these are here. And here you will need to set your global data file, your regional data file, and your hourly data file. There's also an employment module for GENeSYS-MOD, which you can use to calculate job numbers. Then you would also need to specify an employment data file and enable the employment calculations up top. But for us now, it's enough if we have these three files. So if you ever wanted to change these files, then you would just replace this name here, essentially, and then it would read from a different data file instead. On the bottom, you see more technical settings, such as how many threads you want to use on your CPU, what kind of time series aggregation you want to use, what the time resolution should be. This will also be discussed more in the input data workshop, but essentially this is the nth hour that will always be taken. So for 484, it will essentially, if it starts at hour 1, then the next hour would be 485, and then so on. And essentially this would then, in the end, aggregate the year into a time series that has roughly 18 times brackets, right? If we divide 8,760 by 484, then we get 18 time steps in the year, essentially. And you can set this to any number that you want. Common options are 484, 244, for example, then you get 36, 122, then you get 72. Or 73, and 73 is usually one of the preferred options, because if you divide 8,760 by 73, then you get exactly 120 time steps. So essentially this would give you exactly 5 days with hourly resolution. For now, since we want to have a quick computational run and test, essentially, we'll just put it to 484. This is plenty. We could even set it to something lower, like a 1,000 or so, then we would get roughly 9 time steps in the year. We can also define as emission pathway and emission scenario. So emission pathway is usually then something that you can define in your scenario data file for your region. So this regional scenario data file that I mentioned, you can usually define different emission targets, for example, there. These can be called here, and then you can also have different emission distributions, for example, or something like this. At the moment, it can just freely distribute, and I'm not 100% sure whether we have an emission target. We can just quickly check. We might have. If we look in here, then we see that there is, as far as I can tell, no emission target here. Right. Essentially, in order to run the model now, we just need to press the red button on top. So this means run GAMS, and that it will run the model from this file with exactly the setting like this. The only thing that's important to still discuss before we do that is this command line here. This command line is essentially what's being passed on for GAMS as options. And this is quite relevant because that can be used for many different aspects essentially, and can be very useful. This contains exactly the same information as you've seen in the batch file before, right? It's just starting at this point essentially. So it's this batch file is calling GAMS GENeSYS-MOD, and then it passes on all these different settings. So we could essentially, if we wanted to, copy all of these settings in here, and then we would have exactly the same result. But so what do these do? Well, the -gdx command specifies a name for an output GDX file. We can name this whatever we want. We can just call it Middle Earth Workshop. And then in the end, it will generate a GDX file that's called Middle Earth Workshop.gdx. You can give it any name you want. I would always recommend to have this GDX option set, because this will create you a file that contains all the information on your model, completely everything, from inputs to outputs to all the equation information, marginals, everything is contained in there, and you can save this, and then later you will always be able to reproduce your results. You will be always able to essentially retrace what is happening within the model. So this is the biggest tool in debugging and generally using the model. The second option is something that I'm not 100% sure why it's not a default in GAMS. This is essentially telling GAMS to compress this GDX file that you have been generating. Otherwise, the GDX file will be unnecessarily large because it doesn't compress all the 0 elements and so on. So in the end, you will usually end up with a file that's by a factor 20 or so larger than it has to be. If you would put it in a zip file again, then it would be compressed. So then it would be smaller. But GAMS has this functionality built in, so why not use it? So I would always recommend to always have these 2 points in your command line. GDX equals and GDX compress equals. GDX compress equals to 1 and GDX equals to the name of the GDX file that you want to use. What you can also do is, as I mentioned, you can set these switches. So right now I've set here set solver Gurobi. But if I didn't want Gurobi and for some reason I don't want to write it down there because maybe I just want to use the other solver one time, and I can't be bothered to change the file. What I can then do is press -- solver equals cplex. And what this will do is the -- will create this variable here, called solver, with the information cplex. And this will then go to this if statement that checks if not set solver, then set solver to Gurobi. But since we already have set solver to cplex, it will not overwrite this. Instead, it will already know, okay, this has already been set. All right, then I will use cplex instead. So this is just an example of what you can do there. You could, for example, also do exactly the same with switch and of course. This is now changing the stuff up here. Okay, then let's do this here again. So -- solver equals cplex, and then for example -- switch infeasibility tag equals 1. That would then put this switch to 1 for this one specific run essentially. And then, oh yeah, I've named it differently before, but this is like Middle Earth Workshop. Then what you can do is you can just press enter or F9 here. This will then run GAMS. And then you will see a vast amount of lines essentially floating by when the model is actually being built. If you want to slow that down and have a quick look at this before it's finished, then you can press the update button and then it will not float through there again. So what we see at the very beginning. At the very beginning, we see, all right, it is starting GAMS essentially with the following options. So what we see here is then our options that we have chosen. So solver, cplex, switch infeasibility tag 1. Then it's starting the compilation and it's reading in the different data files. So here you will see that it's calling GDXXRW for input data global data.xlsx. This is essentially a GAMS endogenous tool that transforms Excel files into GDX files, and GDX files are the files that GAMS can actually understand. So it's essentially calling this outside tool to transform our Excel files into a GDX file, and then it's reading these files in. It does so for all of the different files that we specified. So it's creating a GDX file from the global data, it's creating a GDX file from the Middle Earth data, and it's creating a GDX file from the hourly data that you will see down below here. Here it's doing the same thing for the hourly data. You will get a number of errors here. So there will always be something like value expected in cell, found Q1N, and so on. And then it will say additional errors suppressed. So we'll get this wide range of errors here. But this is no problem. It will always be 8,760 errors. And this comes down to the essentially structure that I discussed. So if we look at the hourly data again, you will be able to see that we have always this time slice here, and this one contains this information. Well, since we're not using this time slice, instead we're using this hourly approach, GAMS tries to read in data from that point, and it doesn't understand the value Q1N essentially because it's not defined. So we'll just give a warning for this. But in the end, it doesn't matter too much. Everything works as intended. It's just warning you that these values are incorrect, but it doesn't matter too much for us. So you can essentially just ignore these values here. Only if your model run doesn't work for some reason, then you can check this. You can check this quite easily. So if we now go into our GDX files, we will see that now we have a different number of GDX files that have been created. And some of these files are named exactly as the input files, right? So the global data v13, OE stands for open entrance, then my initials, and then the date at which I've created this. So you will see essentially here that these files are created, and here you can check if the read-in has been working properly. So for example, if you wanted to check if the data read-in from our Middle Earth data has been working properly, you can just double-click this or open this via the open dialog in GAMS. It works exactly the same. If you go to GDX file, choose all files, then you could just open it here. And then you will get this GDX viewer, and there you could check if the different values have actually been working properly. So for example, if we wanted to check specified annual demand, and then we can see, okay, all the values that we've seen in the Excel file. So here for Dol Amroth, if we remember, there was 165 petajoules of power demand. It's exactly correctly in here. So there we can use this to essentially check this. But yeah, so it's creating all these GDX files from the Excel file. It will only do this once. So if we run it again, then it doesn't need to do it again because it's essentially performing a check date on the different Excel files. So if you don't change anything in the Excel file, the next time we will go faster. But since we have a pretty small problem here anyway, it's going quite fast anyway. Then it's constructing all the different equations. So now you will essentially see that it runs all the different equations. Then runs this time series reduction algorithm. The time series reduction algorithm contains a nonlinear program, which is essentially used to transform this time series. So here you will see then IP-opt, which is used. For this problem, it will essentially perform this time series reduction, and then it will pass it on to the actual model, and then you can see all the different equations are being constructed. And when the different equations have been constructed, then it will pass it on to the solver. And then the solver, in our case, since we've specified it as Cplex, Cplex will get a different number of options, essentially. You can change them if you wanted to. But these are different Cplex options that are being set. For example, one of them is the number of threads that we can set on the top. And then it's passing this on to Cplex in order to optimize the model. And then it will optimize the model given the different information that you have given it. And in our case, it took only roughly 7 seconds to solve. So that was really, really quick. Since we only looked at 1,000 hours. So that's only 9 time steps, as I mentioned. That's very, very quickly. Then we'll tell you optimal solution found, objective is something. And then what you will always get, and this is what you will always want in GAMS, is the line normal completion. So these are the things that you need to watch out for. If you've ever solved a model in GAMS, you want to have normal completion, and you want to have from the solver optimal solution found. It might look different from solver to solver, but in the end, you want something like optimal solution and normal completion. These are the two things that you always want. Then we get an output GDX file, as I mentioned, and for us that's called Middle-earth workshop.gdx. It will always be in your main directory, so it will always be in the main folder where you've run your model. It will be here, Middle-earth workshop.gdx, but you can always open it by simply double-clicking it here. So you will see it here, GDX file, Middle-earth workshop.gdx. You can just double-click it, and as I mentioned here, you will find everything, so all sets, all parameters, all variables, all equations. And here we could, for example, then very easily check what the emissions are in total. For example, model period emission limit, and then we would see in total we emitted 37,865 megatons of CO2. So CO2 is handled in megatons, so in total it would be 37 gigatons of CO2. And then we could essentially check the different entries for all the different constraints and so on and so forth. And then things that we could check as a variable, for example, would be production by technology annual. And there we could see, for example, power production by hard coal power plants is quite high in Gondor and Mordor, but is then phased out over time, and essentially in 2040 no pure hard coal power plants are being run anymore across Middle-earth, for example. So you can always use the GDX file to directly look into the results. Of course, it's only number based, so it's only tables, but still the GDX file can be very useful to troubleshoot your problem, because as I said, you have all the information in there. So it's always good for a first glance. Otherwise, it's usually easier to use the CSV files that are being produced at the end of the model. Speaking of these files, you can choose at the end. There's a switch, which is called switch output, and currently it's set to GDX. This means that in the end, you will only have a GDX that's being output, which is, of course, probably not sufficient for everyone. So in our case, we can just change this to CSV. We can just change this to 484, then it will calculate for a second longer, but we can just press go again. And now we will run the model, but instead of with every 1000th hour, it will be every 485th hour or 484th hour. So now it will run again. But in the end, we've set the write output to CSV. So now we will actually get a CSV file instead of just the GDX file, and that we can use. There are multiple ways of handling the outputs of GENeSYS-MOD. One is always the CSV files that we will get. Those will appear in a second once the model has actually finished. Solved model, perfect. 39 seconds this time. And now it says normal completion after 45 seconds. We got this file, but this time we also have output CSV files. So here you will see the folder was just empty, and now we have different CSV files that are being output here. So we will see something like annual production capacities, emissions, some other values. I would need to check what this is currently. Oh yeah, self-sufficiency rate, for example, is in here, electrification rates of different sectors, final energy consumption. So these kind of information, you can find them in the CSV files. And you can, of course, then read in these CSV files if you want, as you want, to any kind of program that you would want to use. So that's actually quite easy. The issue why we are usually using a different method and using Tableau for this is because this is then a little bit more tricky if you want to compare multiple runs. Because of course, every time we run this, we will get a new set of files. So in our case, we got these files here, right, for Middle-earth global limit CSV. But if we wanted to do a new run, which is then maybe not with the emission pathway Middle Earth, but Middle Earth, I don't know, Middle Earth low or so, I don't know, if we defined this emission pathway somewhere, if we wanted to run this, then it would create a new file, but these would be two separate files. And this is why we actually like to use the GDX files instead. Because what you can do is, like, now we've calculated with 484. We can now calculate it with 1000 again. And if you wanted to have a look into how the different results compare, then it's actually quite useful to use the combination of essentially the GDX files and Tableau. It doesn't have to be Tableau, but in general, using the GDX files is then quite handy. So now, after we've run this only takes 19 seconds in total, we now have two GDX files, right? We have the workshop, which contains the 484 resolution, and the 1000 one. And what we can do is we can just copy those to the results Tableau folder, and we can place the two GDX files in here. And if we look at this merge file, what this merge file does is it merges all the GDX files in this folder. It merges these variables, or essentially outputs, from the different GDX files, and then it puts them into CSV files. So if we just run this, then it will tell us that it will merge the GDX files. It will include these IDs. We've just seen them in the batch file. It will output this into merge.gdx. And then it will essentially say merge complete, two input files merged, and it will list the files that it has merged. So it has merged Middle Earth Workshop and Middle Earth Workshop 1000. And then you see the different CSV files that are being generated. So you see essentially annual energy balances, energy balance, and so on. So you see exactly these files, or mostly these files, even a couple more files than before, that we've seen in the different result directory. And one main advantage now is that you can do this with any number of files. So even if you had a large-scale sensitivity analysis of thousands of different sensitivities, you could very, very easily just put all of them in the folder, press merge, and would put all of them together, and then you can analyze them. And of course, since it's CSV files, you can just do it in Python again, or you could use something like Tableau. I will very briefly just show this. So if you open Tableau, most likely it will say something like there was a problem connecting to the data source. This is because it's always linked to an absolute path and will not find the file. So you can just press exit, and then it will offer you to browse for them. So for me, it's in desktop, GENeSYS-MOD Middle Earth. It's here, and then it's in Tableau. This is what we just generated. And then we can just press open. Then it will open everything. And then we will see that in my case, the CSV format was not correct. So in my case, I need to change this to be field separator, comma, and then everything will work again. It's sometimes a little bit wobbly in that regard, that it sometimes, due to your regional Windows settings, it might expect a comma, or it might expect a semicolon instead. In our case, we want a comma. And I have to do the same again for this file. Most likely I will have, I don't have the exact same problem. And now if I look at compare power, for example, I need to remove the region Norway because we don't have a region Norway. And now I can look at the different graphs. And here I quickly need to check, this here is gas HP, so I need to group this. No idea why this wasn't grouped before. Right, but if I look at this now, this is then essentially the graph for generation and consumption of electricity. So this is for the fuel power for all the different regions. We could look at a specific region like Dol Amroth, for example. But yeah, Tableau is very useful in a way that it's very easy to generate graphs, especially from very complicated data sources. And in this case here, we already have a predetermined Tableau file. You have already downloaded this, so you can very easily just open this if you have a Tableau on your system. And what we can see here is then for the different technologies, how they essentially compare. And this one here is the 484 resolution, and this one is the 1000 resolution. And there we clearly see a huge difference in generation. For example, here in the 1000 resolution, we have much more solar power compared to the 484 resolution, where we have then much less solar power, instead much more offshore wind and also onshore wind. So you can see that you can use this very easily for sensitivity analysis. If you run different settings for the model, and you don't have to go into the input data, even you don't have to go into GAMS code. The only thing that you need to do is essentially play around with these switches that are being provided, and then you can already create a first set of essentially sensitivities, right? You can very, very easily play around with this, change the time resolutions, change different parameters here, and you can already use this without ever touching GAMS. And if you wanted to look then at different effects of demand developments or so, everything that you would need to do is essentially go into the input data, change the demands here, in the data Middle Earth. You would just go into the specified annual demand. It's probably up top here somewhere. Yeah, you would just go into the specified annual demand. You would set this value to 300 if you wanted to have it 300, and if you wanted to have the demand flat instead of reducing, you could just do this, save the file, run it, it would work. It will give you outputs. You can just use this for sensitivities. And as I said, you will get CSVs out of there that you can read into any kind of program. But using the GDX files to create merged CSVs, and then using Tableau is just very useful because you can very, very easily create graphs, also maps and so on. I can also show this in the further workshop. Right, we can just save this if we wanted to. Okay, so this is essentially a very brief overview into how to get the model running, all the files that you need, the software that you need, and some tips and tricks on how to run the model in general. The next workshop will go more into the field of adding something. So there we will add specifically a technology and a region, I believe. We can quickly think about this. Yeah, adding regions and technologies to GENeSYS-MOD will be the second workshop. So this is going to be another lecture where I will go a little bit more into how to expand the data set if you wanted to add regions, add technologies, change technologies in general. This will be a separate workshop. But by now you should at least, as I mentioned in the beginning, be able to understand the basics of the model structure. You should be able to run the model in the local machine. You should know how to iterate over some key model settings. As I mentioned, the other part, we haven't gotten into this one, but I can quickly show this. The other part would be the GENeSYS-MOD settings. So here right now, the year 2035 and 2045 are disabled. We could just, for example, say, okay, but we want these years. We could just enable them again, just by starring it. It's a comment. You could either do no and then comment it out, or you could do yes. That's what you could do, right? You could either comment it out, or you could change the no to a yes. And now if we ran it, if we do not 1000, but intermediate years, we could just run it again, and then it would have the intermediate years included as well, because our input data, if we look at the input data again, then we will see in our sets, we actually have data on the years 2015 to 2050 on 5-year steps. So essentially 2035 and 45 were just disabled in the model and just ignored for the model calculation. So now, for example, we will have results for all the different years, for example. And these are things that you can very easily play around with without ever touching GAMS in a detailed fashion. So now if we look at the set year, then we will see now all the different elements are in here. Don't worry about this line here. This is mostly GAMS doing some gibberish. That's not very relevant. The important part are the entries on the left-hand side here. And you see now there are 8 entries. If we look at the file that we had before, there we only had 6 entries. So 2045 and 2035 were missing. And now we could do exactly the same thing. We could just put it from here in the Tableau folder, press merge, and then we would have it in our CSV files. So it's very easy to do. Very easy to play around with to get a first hang of the model. And essentially any kind of GENeSYS-MOD version, be it this very small and simple Middle-earth example, or a more complicated one like the European application from the Open Entrance project, works exactly the same way. You can just download it, go into the GENeSYS-MOD GAMS file, and usually all the settings will already be pre-provided. You can then usually choose between the different pathways or so, but in general, everything will already be there. It will work, and you can just run it and do your own calculations. You can validate the results that have been published, and you can do sensitivity analysis. These can be done very easily. A little bit more in depth is then adding new regions, technologies, creating your own data sets from scratch. That's a little bit more tricky, but this will be covered, at least in part, in another workshop. So now we should have covered everything that was on the list. I hope this was helpful to you. If you have any questions, you can always contact me via email at kl@vip.tuberlin.de. I will try to answer as soon as I can. We also have the public GitLab page. We will also have a GitHub page for our new model version, which includes the Julia version. There are Zenodo repositories for data available that you can just use to download input data sets for GENeSYS-MOD. And apart from that, I hope this was useful to you. I hope you learned something. This video has been created in cooperation with Sintef Energy in Trondheim and has partially been funded also by the Research Council of Norway, who have funded a research stay there. So I have to give a shout out to them and thank them for everything. I think that was actually it. So thanks for watching, and I hope this was useful, and see you in the next workshop. Bye.